from outside the FLEXYNETS project. They are Herman Idams and Christina Lignerud. So they will speak also about other projects still strictly connected with FLEXYNETS activities. So let me then start with my first presentation. I will provide an overview of the results of the FLEXYNETS project, trying to highlight the connections also with the electric sector. I remind you of the FLEXYNETS website, where you can find information about all the project activities and download the public deliverables. I will explain you the project content and how the project was organized, again focusing on results. So before introducing FLEXYNETS, I think it's useful to recall the starting point, which is traditional district heating. Traditional district heating is seen as a very positive technology within the European energy agenda. It provides a higher efficiency than individual heating, as it can integrate waste heat and already available heat without having to burn additional fuels, let's say. However, also it includes some drawbacks. It's typically performed at a relatively high temperature, with a supply temperature of 80-90 degrees and return temperature of about 50-60 degrees. So with a temperature difference between supply and return of 30-40 degrees. And with these distribution temperatures, of course, thermal losses are not negligible. Moreover, the fact that the temperature is so high prevents the possibility to integrate some available heat sources which can be found within the urban context. So in the light of these observations, it is interesting to try to find new solutions. There is a general trend within the research in this field for the lowering of operating temperatures, and within the FLEXYNETS project we wanted to push this concept somehow to the limit, working at what we call neutral temperatures, so temperatures of the order of the ambient temperature, about 15-25 degrees, so also with lower supply temperature differences, but with the possibility of directly and easily integrating all the low temperature waste heat sources which can be found within the urban environment, and also to achieve an easier integration of some renewable sources. So within this picture we try to highlight that it is no more something exploiting like incinerators or traditional CHP, but also a technology addressing waste heat coming, for example, from refrigeration units within shopping malls and so on. Integrating different energy sources of this type requires some changes and even an enhancement of the communication possibilities. And moreover, on the consumer side, we plan the possibility to have a bidirectional heat exchange, because with such low temperatures, of course, it is not possible to directly heat houses. A heat pump is needed, which becomes the key ingredient of residential substations. On the other hand, reversible heat pumps are available, so that this type of solution is suitable also for the integration of cooling, for the creation of a reversible network, exploiting the same pipes for both cases. This bidirectionality, of course, introduces some new features in the control and in the monitoring of substations, which is one important work package within this project. So heat pumps, of course, need electric energy to work, and this provides this very strong link with the electricity sector. Electricity is typically more valuable than heat, so it comes at a higher price and also involves higher emission factors. On the other hand, there is a clear decarbonization trend within the electricity networks in Europe. You can see here a graph for a few countries: Denmark, Spain, Italy, Germany, and the average for the EU 28 countries, with a clear decreasing trend. Moreover, within FLEXYNETS, with the available network temperature, the performances, so the coefficient of performance, the COP of heat pumps, is expected to be very high, of the order of 5. So this provides an interesting coupling with the electric network, without relying too much on this type of energy source. The partners involved in the project are shown in this slide. Europe was the coordinator. Planenergy is a large engineering office in Denmark. Acciona is a big Spanish partner. Ensist is a German partner focusing on control. Soltigua is an Italian partner producing concentrating solar collectors. And then there is the University of Stuttgart, involved in a lot of simulation activities. So this consortium tried to rely on this methodology with, let's say, 3 pillars in terms of activities: simplified techno-economic estimates, simulations, and experiments. Concerning the project content, the core of the project comprises these 3 work packages. So we try to focus on substations, which are of course the key components connected to the network, on the analysis of the system and the network, and on the work on control, which requires some changes with respect to traditional solutions. All these activities were also applied within laboratory tests. 2 laboratories are available within the project consortium at EURAC and at Acciona. I will not, however, focus much on this point during this presentation. Of course, the project also gave space to exploitation, dissemination, and communication activities, with some interesting outputs available to the public, which will be mentioned later. So I will now try to summarize the main points concerning these 3 core work packages: substations, network, and control, starting from substations in work package 2. So the word substations in the FLEXYNETS context is something we used for all the components connected to the network. So substations in traditional networks or also in the electric grid typically refer to points where there is a transformation of the energy level from a high level to low level, for example, from high voltage to low voltage in the electric grid context, or from high temperature to low temperature in traditional district heating networks. Here, however, having also bidirectional users, the concept of substation becomes a little bit more general. First of all, we can have prosumers, similarly to the case of the electric network with photovoltaic plants. So buildings can both absorb heat from the network, but also reject heat to the network, so becoming both consumers and producers. So from this point of view, substations are not simply points where heat is extracted from the network, but also points where the heat is supplied to the network. Of course, it still makes sense to distinguish between residential applications, let's say, and larger substations, basically power stations, which supply the majority of heat to the network. Yeah, a more general concept than traditionally used holds here. So you see here in this slide some sketches of the components used for residential substations and a possible CHP concept we'll mention in a while. So concerning the residential case, of course, the key ingredient is the heat pump. That's the core around which the entire substation is built. This is the layout we used in FLEXYNETS for simulations. I would like to point out the connection to the network with a recirculation circuit. which can be important to adapt the temperatures to the operating conditions of the heat pump. This is not the only solution which was studied within FLEXYNETS, but it is the one which seemed to be the most promising one, and which could in principle allow also the network temperature to fluctuate even more than the 15-25 degrees I mentioned before. On the side of the building, which is on the right-hand side of the heat pump, it's important to stress the presence of local thermal energy storages, especially the one for the domestic hot water preparation. This is a key condition when one has a heat pump, because instantaneous production of domestic hot water is not very so easily possible with a heat pump. So this requirement becomes also an opportunity, because the availability of this thermal storage allows for a flexible scheduling of the heat pump operation, enhancing the connection with the electricity grid, and even making possible the application of demand-side management strategies, as will be mentioned later also in the presentation about control by Dirk Pietruszka. The connection with the rest of the heating and cooling circuit also in this scheme includes a small buffer, but this is less mandatory, let's say, for the operation of the system. I also emphasize that in this scheme we didn't include explicitly a backup. This could be a possibility. Heat pumps are often coupled to backup units like gas boilers or electric heaters, in order to limit their size and possibly reducing costs. But we also wanted to stress that it's possible to operate even without these backup units, which is of course something important in the cases, for example, where one really wants to get rid of the connection to the gas network, or one wants to avoid as much as possible the consumption of electricity. Concerning power stations, this is an example of the work we did. We had a special focus on the, let's say, evolution of the combined and heat and power concept, so the CHP concept. Of course, several and traditional also sources can be imagined. So this is just one case, but it is interesting to stress that traditional CHP is not the best solution to be coupled to this type of network. Indeed, even if a lower temperature network can be beneficial from the point of view of cogeneration cycles, because a lower condensing temperature increases the electric efficiency of the engines, the presence of heat pumps requires the consumption of additional electricity, so that the overall balance of the system makes a little bit questionable the use of traditional CHP units within FLEXYNETS. So we wanted to revisit a bit this concept and at least increase its renewability. This is why we wanted to include concentrating collectors and biomass boilers coupled to ORC engines to provide a concept which is similar to CHP but relies on renewable energy. The amount of equipment involved in this solution and the high investment costs involved make this solution viable only in a few cases, but still it can be something applicable. The last point I want to mention about Work Package 2 for substations is the concept of seasonal storages. These are crucial systems in order to make a good energy balance throughout the year. They are, however, very recent solutions, not cheap, let's say, from an economic point of view. A few solutions can be pit storages, aquifer storages, or boreholes storages. We will have a special focus on this topic by Daniel Trier from Plan Energy, so I just wanted to mention this. Summarizing our activities on substations, I would like to leave you with some messages. So concerning residential substation layouts, we pointed out the importance of a flexible coupling with the network, possibly using recirculation, and hence allowing for higher temperature fluctuations within the network, thereby exploiting also the buffer potential of the network, and the importance of local thermal storages also in view of demand side management strategies and providing some storage for the electric grid somehow, thanks to the use of heat pumps. And concerning power stations, as I just said, the possibility to substitute traditional CHP with solar CHP, let's say, which can be viable under some specific conditions. All of these analysis was done with detailed simulations, and one of the outcomes of the project was really to provide a simulation database, especially for user profiles connected to residential substations, which is one of the important ingredients for network simulations, which I'm going to mention now. Two deliverables are available at the FLEXYNETS website concerning this, so FLEXYNETS substations, and the deliverables are a report about large storage systems for DHC networks. So the next pillar, let's say, of our analysis is the analysis of system and network. This included the analysis of network layouts and of the overall urban context where these type of networks can be installed in order to let's say review typical heat densities within cities, and also to analyze the possibilities to recover waste heat within the urban context. Then a crucial step was the realization, the implementation of a detailed network model, which was done by ZAFNet, by the Stuttgart Hochschule für Technik, and the preparation of a pre-designed tool for the quick analysis of system scenarios, since the network model is very detailed, but more suitable for detailed analysis of single networks rather than an extensive parametric analysis of multiple scenarios. So concerning this pre-designed tool and scenarios, there will be more in the presentation of Plan Energy. I want to mention here just the network model and some of its details. It's a model built within the Transys software and available also within the INSUL software developed at ZAFNet. It includes two main modules, a hydraulic module where the flow rates within each network branch are calculated. The solution is based on the Kirchhoff laws and on a graph theoretical implementation, taking into account all the vertices and edges of the network representing pipes and substations. And a second module, which is the thermal module, where instead the temperatures within the network are calculated on the basis of an energy balance approach. So in this way, one can perform yearly simulations, for example, with a 5-minute time step, so quite detailed for relatively large networks of tens of substations. So these two outputs, the detailed network model and the pre-designed modeling tool, are the main outcomes of this work package. And again, there are two reports available at the FLEXYNETS website. Actually, one is already available, the analysis of networks, network layouts in selected urban contexts, and the second one regarding the integration of substations into DHC networks will be available soon. So the FLEXYNETS project is going to be finalized within this month. So in January, you will have these reports available. So the last last key work package is the one about control, where the overall network control was studied, but also advanced control solutions from the point of view of supply units and residential substations were studied. The key approach here is the one of model predictive control, which allows for an optimized control of the considered system. Control involved also some practical applications within the laboratories, especially the laboratory of Europe. This will be explained more in the presentation by Dirk Pietruszka of AnySystem. Here, let me just briefly summarize the concept of model predictive control, at least for the case of substations. The idea here is to have a model which allows to predict the evolution of the system in order to optimize control. So our approach was typically to have a very detailed model of the system we want, for example, the Francis model of substations. This is a rather heavy model, so something which takes some time to run and which is difficult to be included within an optimizer. So it was then used to train an artificial neural network, which provides a much faster implementation of this model, which was the ingredient actually used within the optimizer. So running different control configurations until the best one is found, and so that the system control can be established within a given horizon, then updated case by case. So again, the results I mentioned are the most important ones from this point of view. AnySystem will tell you more about this. And again, some deliverables are available on the FLEXYNETS website from this point of view. I will go very quickly through experiments. So results about experiments are not publicly available on the website, but feel free to contact us for more details. We have laboratories implementing basically all the equipment considered in the FLEXYNETS project, both at URAC and in Acciona. The URAC laboratory is more focused on the network, and we would be glad to provide you more information on this. Just a quick mention to some, let's say, innovations introduced by Soltigo and by AnySystem. So the FLEXYNETS loop, which is a kit for an improved operation at the balance of plant level for the solar field collectors, which can extend their operation, and the innovation about FLEXYNETS control, including a new software and a new hardware developed by AnySystem during the project. Let me quickly point out some dissemination activities which are still ongoing and which will be made available on the website again in January. An educational kit is already available, but we will have focus on trading on some case studies about early adopters. 3 networks expected to implement the FLEXYNETS concept will be described there. There will be a guidebook and the pre-designed support online tool, which will be mentioned more in detail by Daniel Trier from Planenergy, will be made downloadable from our website. So that's a very extended Excel tool which allows to estimate the FLEXYNETS operation. So there will be also more discussion about business models and low temperature waste heat within the presentations by IVL and Minwater. So it was a pleasure to give you this introduction and this overview of the FLEXYNETS concept. And now I give the word to the next speaker, which is Daniel Trier from Planenergy. There is, I think, yeah, we are on time, let's say. So I just stop presenting and give the word to Daniel.
Thank you, Marco. And you should be able to see my screen now. So I will explain to you about the network structure and long-term storages in this kind of networks. And a brief agenda from my presentation is a quick introduction of why are we even considering this to be a relevant concept. Then about the different thermal storages. This is about large-scale storages and different types and the pros and cons for these. Then something about the network analysis we did methodology examples and different configuration options. And at the end, I'll explain about a parametric study we did on investigating what are actually the different main aspects of this concept in terms of making it potentially feasible in the future to compete with alternative options. So with this, I will just say, well, as a first starting point is that the energy system transition indicates that in the future we will have much more renewable energy. And when we think of this, it's also important to keep in mind that it's not only the demand we have today, which needs to be replaced with renewables, but actually we have an increasing demand, for example, from data centers needing a lot of electricity. Bioplastics is something coming in the future, and of course also the transport sector is a hot topic at the moment, with an expected increase in terms of electric vehicles, for example. So we have to keep in mind that we need a lot more green electricity and green renewable energy in general. So with all this increasing fluctuating renewables, for example, wind and solar, this will require some flexibility to keep the balance in the networks. And what we can see also from other studies is that district heating and cooling, together with cheap thermal storages, can provide a lot of that flexibility. So this is just to highlight that the sector coupling between electricity and heating and cooling, together with flexible demand, can really make it possible to integrate a lot more fluctuating renewables in the system. And this also includes the use of power to heat, meaning heat pumps, for example, together with the thermal storages. So the considered storages in this analysis we did is tank storages, large-scale tanks, pit heat storages, boreholes, and aquifer storages. And we took some different examples of real costs to get an idea of the economy of scale of the different types. What we can see here is that there are significant differences between the economy of scale of the different type of storages. A few examples of some of the storage types. This is a borehole storage, where on the top right we can see a principal sketch. This is the borehole field seen from above, and where we can see the different connection between the different boreholes in series, where different boreholes are connected. For example, 6 boreholes in series, and then jointly connected, all of them in the center. And on the right-hand side at the bottom, we can see that this specific example is boreholes 45 meters in depth, and the 59 meters is a reference to how deep the measurements are done, just to keep track of the temperature in the soil, also below the boreholes. A few images of the construction phase. Maybe a curiosity here is that the insulation material chosen is actually mussel shells. So we gathered from a nearby shore and just washed and then used as very ecological insulation material. So mussel shells turned out to be actually quite suitable insulation material. So this was chosen, and on top of this is then soil, and today we just have the only visible thing is the center access point to the center well, and then there are just grass field where you can utilize this area for something else today. This is one of the main benefits of the borehole storage, that you can use almost all the area for other purposes. Then another type of storage is the pit heat storage, where you can, let's say, in principle, dig a hole in the ground and put the soil on top of the sides to make the depth a bit higher. Inlet outlet diffusers in different heights, so that you are able to extract heat at different temperatures. That you have the high temperature of water at the top and the low temperature at the bottom. On top, you'll have a floating lid, which is insulated. And here's an example of the construction phase where we have the inlet and outlet diffusers in here center. And you put a plastic liner, keep it watertight. And we have some more detailed information also on the construction in the report, which is available on the website. I won't go into these details today. On the top is used some pipes just to keep the weight down, and this is in order to avoid rainwater puddles forming different places on the lid. So in order to control where is the rainwater going, these weight pipes are put in, which means that all the water will be gathered in the center part of the storage lid on top, and then from there it's pumped away. This is all done automatically. It's turned out to be a cheap solution. And this specific example is from Denmark, and it's around 60,000 cubic meters of water. So one of the drawbacks of the FLEXYNETS in terms of these storages are the low delta T. So of course, if you have 1 cubic meter of water, it's very important how big is the temperature difference if you want to consider how much energy do you store. So the smaller the delta T, the lower amount of energy you have in a specific volume. So it is a relevant technology to include also in the FLEXYNETS concept, but it becomes more relevant and more feasible if you have access to somewhat higher temperatures, for example, waste heat that you can use directly in the storage. So one thing we also notice is that if you have higher temperature waste heat, instead of injecting that in the network and then applying seasonal storage also connected to the network, you might be better off to connect the seasonal storage with the high temperature waste heat source directly. This will, in some cases, mean that you need a transmission pipe to connect the two, but still the cost of a transmission pipe is not big enough to make it unfeasible compared to storing at lower temperatures if you connect via the low temperature FLEXYNETS network. So in general, if you want to apply, for example, PT storage, you should try to do that with higher delta T than the FLEXYNETS network. So we did different model scenarios here, and this was just one example of applying bigger and bigger volumes of the PT storage. And what you can see with the bars is the total cost of supplying the heat. And in the first 5 columns, 5 examples of increasing storage volume, you will see that the overall cost is more or less the same. But the gray bar is decreasing. This is the fuel costs of the network. Whereas the blue bar is increasing, which is the capital cost of the PT storage. So in other words, the cost of the storage takes over for the cost of fuel, which means that your overall cost is more or less the same. But as you can see on the secondary axis to the right, also with the blue, with the black markers, is that the CO2 emissions is decreased significantly. So if your purpose is to decrease CO2 emissions rather than decreasing the costs, maybe this is one way to go. We have further information like this also in the report. So some key conclusions in terms of the storages is that for the tank storages, this can be a fairly simple solution and can be applied almost everywhere on top of the ground, and it might be the cheapest option for smaller volumes up to some thousands of cubic meters, a few thousand. The PT storage is able to store also at higher temperatures than the following two, up to around 90 degrees, and could potentially be the cheapest option if you go for really big volumes. A benefit of the borehole storage is that the area can be used for other purposes as well. And compared to the aquifer storage, you have a closed loop, so you are not that dependent on the specific geological conditions. Again, also for the aquifer storage, the area can be used for other purposes, a benefit compared to the pit heat storage. And also you can combine the heat and cold storage, and potentially it can be quite cheap. So when comparing also to conventional district heating, one thing to keep in mind is that drawbacks for the borehole storage and for the aquifer storage is that you need a heat pump to extract the heat if you need conventional district heating supply temperatures. But since the FLEXYNETS network does not need that high temperatures, this say drawback is diminished or eliminated. And for the pit heat storage, if you have higher temperatures heat source available, this might be a suitable option. So for the network configuration, just a principal sketch here of where you have the supply line here in red. And as you can see, most of the heat pumps in wintertime would be used in heating mode, meaning that you extract heat and then the return line will be a bit colder. If you have some heat pumps in cooling mode, you might inject some warmer water in the return line, but this will be a minimum or almost eliminated in wintertime, so the impact will be almost nothing. In case you have some waste heat, you could inject that heat into the supply line as well. And if you need to apply some extra heat to the network to balance the load in general, you could supply that with a centralized heater. Similarly, in summer where your main demand might be cooling, the main purpose here would be having a supply line here and then inject your excess heat from the cooling processes into the return line. In this case, your excess heat will not be injected, so that's just wasted. And you might need a centralized chiller instead of a centralized heater. But one thing is the principal sketch. Another thing is that the demand densities of the different areas is quite important. And here's just an image of the red area is just the chosen geographical area that we investigated and checked what are the different demand densities across such a town. And what we can see here is that the different blue areas represents mainly residential areas, and the darker blue, the higher the density. So as you can see here, the main urban area is the central part of the town. Orange and yellow is industries, and green is parks and other places where you don't need heating. So this is just one example of how we have checked different towns and what are the variety of demands within a town area. And what we did, we used this to investigate what is the cost of the FLEXYNETS network and how could the network be constructed in terms of the layout. And at all times, we tried to compare with conventional district heating just to get a feeling of what would the let's say reference situation be in terms of existing district heating or conventional district heating applied. And we investigated also both a ring structure and a branch structure. I'll show you an example in a minute. And what we did was including a lot of, let's say, properties as inputs, pipe types and capacities of these different diameters, heat loss, numbers for that, and investment cost and so on. And this was then combined with demands of the different buildings in the area. And from this, we then applied a GIS tool and to investigate the grid lengths needed, also from the different diameter, and the heat losses and investment costs and so on as a result of that. Here you can again see the different typologies, different demand density areas. And when we applied the tool, we can then get an overview of the different diameters of the network we need to supply the demand we know of that area. In this case, we have the ring structure in the orange one, and the different green points are the connection points And then we compared with the alternative option, which is the branch structure, where you would need, as you can see here, the darker blue colors is the bigger diameter, bigger branches, bigger pipes. Bigger pipes are needed from a centralized point of view in order to reach even the furthest outskirts of the town. So this is just to show you examples of our analysis. Coming back to this, flowchart, we can then use also this to add what is the cost of the heat production units, what is the fuel and maintenance cost, the heat pumps cost, and so on, electricity prices, and this is then used to apply a calculation to get a complete overview of the costs for the whole demand. Not only operation costs, but also capital costs.
Daniel, a very short interruption from my side. So there are no questions so far, so I think you can use all the remaining minutes to present the remaining slides. 5 minutes remaining.
Yeah, thanks. So in general, one key outcome is that we can see that the feasibility of FLEXYNETS is really depending on the ability to use excess heat. And of course, there will be a lot more excess heat potential when you consider lower temperatures than high temperature. Also, a ring structure requires a certain amount of excess heat to be reached by the ring or very high density area in order to make that feasible compared to a branch structure, which might be more common. Also, you should consider that hybrid solutions are possible, meaning that you could, in principle, connect a FLEXYNETS area to existing network using, for example, the return pipe of the existing district heating network as is applied to a FLEXYNETS network. And we can see that this concept might be maybe more relevant in the future, where we will have increased cooling demands, increased requirements for flexibility, lower temperature requirements in the buildings, and more focus on utilizing excess heat. And as mentioned in the beginning, also more fluctuating renewables providing, in some periods of time, cheap electricity, again requiring a flexibility in the demand. So in order to investigate what are the most important parts of the costs for the different components needed, we have the network, we have the different substation units, the different heat pumps at the consumer site, or prosumers, we should say in this context. Then, of course, the electricity for the heat pumps, electricity for the pumping of the network, the main heat supply, and operation and maintenance costs. So what I can show you in a minute is a breakdown of cost for the overall network. So in this parametric study, we varied a lot of different parameters to check what are the most important components of cost and what is most important to focus on if you want to make FLEXYNETS feasible. And one example shown here is when you have the lower temperature of the FLEXYNETS, well, you would have lower heat losses of the network and or lower insulation material possible, which is positive compared to a conventional district heating. On the other hand, the drawback is the lower delta T, meaning that you would need a higher flow rate for the same thermal power in the network. Then again, a positive thing for the FLEXYNETS concept compared to the conventional district heating is that you have more options for excess heat. And another drawback is that you need heat pumps at the end consumers, as Marco mentioned, which increases the investment costs. A benefit then again is also that you can utilize the same network both for heating and cooling, which leads to the comment that, of course, the feasibility also depends on, do you really need the heating and cooling at the same places? So this is just one example of a lot of different pros and cons just from the focus of lower temperature. An example of from the parametric study is here seen where you have the breakdown of costs, and I don't want you to go into all the different details, but This is just to mention that you have the patterned red area here is, oh, sorry, the big majority is the fuel costs in the conventional district heating. The blue colors are for the individual cooling units applied. In this case, you have 25% cooling demand compared to the heating demand. DH is conventional district heating. In the FLEXYNETS concept, you have a lower cost for the centralized heater, but then you have very high costs of substations, meaning the heat pumps at the consumers, and then of course some electricity for these heaters. The cost is in general decreased if you get some excess heat, in this case 60%. Still, it might not be enough to make it feasible. But then again, if you have a higher share of cooling demand, conventional district heating plus individual cooling units might reach this high costs. And then if you then have some share, in this case 60% waste heat available, you'll actually reach the same cost levels. So in general, what we can see from this is that the electricity for the substations, meaning the heat pumps, together with the investment cost of the heat pumps, is very important for the FLEXYNETS feasibility. But at the same time, if you look at the patterned red area, this is also one option of really decreasing the centralized heater operation. And if this is a gas boiler, for example, this is really a way to potentially decrease your CO2 emissions. Quickly going to an example of applying seasonal storage or not. In this case, we can almost eliminate the centralized boiler operation by applying the seasonal storage to utilize more waste heat. But then again, the brown here area is the cost of the storage. So in principle, this example shows that it's not feasible to apply the storage, but on the other hand, you might have CO2 emission reduction targets, which means that you would still go for this acceptable cost increase. So a few couple of slides is to conclude that the FLEXYNETS concept is likely to be competitive compared to conventional district heating if you have low electricity prices and if you're able to lower the heat pump installation costs and a cooling demand so that you can utilize the network both for heating and cooling. Waste heat is really one way of lowering the overall costs. And in turn, you can also get lower CO2 emissions and primary energy use by, let's say, circulating the same heat within the network for both heating and cooling. So last slide here on energy system transition trends is that in the future there will be many more consumers, prosumers, meaning that we will have a much more decentralized and diverse energy system interacting between different sectors. Previously, in the energy system, we had a lot of focus on operation costs, meaning the fuel cost with potentially cheap boilers, for example, with a low capital cost. And in the future, we'll have probably a bigger focus on capital costs and in turn lower operation expenses, meaning that we'll have maybe no or almost no fuels, but the cost of heating and cooling will be used for the investment in the components. We might also see a stronger focus on selling the service in the unit, meaning that a centralized utility would make sure that you get what you need in terms of heating and cooling, and you should not consider too much on maintaining your own system. This is all taken care of. And with these trends, you could say that FLEXYNETS takes this to the next level. There's an even increased focus on the capital cost because the investment is bigger, but in turn you might get even cheaper operation expenses, and you could use your local resources for example, waste heat. Also, you have a flexible interaction between the sectors, both heating and cooling and electricity. And you could also consider this as an option to selling the heating and cooling as a service, where the network manager chooses the optimum operation strategy, optimal network temperatures, for example, to consider the network as a whole, both for heating and cooling demands. And as a final point here, this is an EU project, but you should also consider that this concept might not be only relevant for the European countries, and with the expected increase in demand for cooling in the future, from a global perspective, this might be actually quite relevant in the future. And this is all from my side. So thank you for
Daniel.
your attention.
Thank you very much, Daniel, for this nice presentation. We are more or less in line with time, just a couple of minutes of delay. So I introduce the next speaker, who is Herman Adams from Mean Water. So he is not within the FLEXYNETS consortium, let's say. So a special thanks to him for joining us with his presentation. So Herman, the floor is yours. Herman, I think you are still muted. Probably you have to.
Okay.
Okay. Now I can hear.
Thank you. Well, my name is Herman Adams. I'm Innovation Manager of Mindwater BV. I will present some work that we did also from Interreg Northwest Europe project called HeatNet Northwest Europe, where we bring a low temperature industrial waste heat into our district heating system. The Mindwater company was funded by the city of Heerlen as a utility company, mainly to reduce carbon burden from the city, and not mainly to make profits. I will address some topics. First, how we came to the Mindwater concept, then how we developed this concept into a third 3.0 version, which we now address as a 5th generation district heating cooling network. What we are doing now in upscaling, and then at the end I will show you some pictures how this shows in the field, what we are doing on works. So first, where we are. I tried, yes, here we are. So we are situated in the city of Heerlen, which is close to Aachen and Maastricht, and in a bit broader circle between Bonn, Eindhoven, and Brussels. The idea in the city was we had former coal mines in this region, about 11 big mines, and the idea was that if we know that temperature is rising as we go further down into the earth, that we could use this kind of water from the flooded galleries and shafts of the mines to heat up buildings, but also if we go to the higher level, we could build some cooling system for those buildings. Well, here I have a picture what we find if we go into those former mines, and we have those shafts. Often they are reinforced, and also the galleries are reinforced, and then we have all these kind of layers filled with grit where the coal came out, and all those voids contain water. So we know from some studies, if we look just at the shafts and the galleries, then we have approximately 2.5% of the volume of the coal production, which would be there existent as water. And if we also take all the other voids in regard, then it would be about 8% of the volume. Well, this is a picture of such a gallery. There were trains running. It's about 2.5 meters broad and 2.5 meters high. And we can take this water from this gallery. And then if we want to know how much energy is there, we have a temperature difference of 12 degrees. So 1 liter water would bring us 14 watt hours. On the other hand, if we look at thermal storage, or if we even look at the energy storage in a broader way, then we could compare that about 6 cubic meters of water would contain the same amount of energy as the battery of a Tesla. So somehow we would have 1.4 million Teslas thermal capacity from this former mine under our feet. And if you tell these stories, then people start understanding what it means, what kind, the volume of energy that you can bring there. Our first approach was to take this hot water from a deep level, bring it to the buildings, and then we had a return pipe which would inject the water again somewhere at 500 meters deep. And in summer we would take cold water from 250 meters and again return it at the 500 meter point. It would flow through the galleries, which is a kind of labyrinth underground, to back to the extraction point, and then cool down again or heat up again. This is a concept which takes geothermal energy as a source, and from this concept we made 5 pits and can take about 4 megawatts of energy from the mines. When we further developed it and we came to the point that we needed more energy in the city, but needed more connections to get a proper business case, but we were not able to drill more wells in the mines, then we started to think about recharging these sources, and we switched our system. So now we have the heat source at 700 meters deep. We take out energy in winter and bring back in summer. And we have the cold source where we do the reverse thing in summer, take cooling and bring it back in winter. Well, this is an overview of the city of Heerlen, where we are active. We have the yellow line, which is a mine water backbone connecting those red points and blue points, which are our pits and wells. And we have our return point in the middle. And then on this backbone, we developed clusters of buildings. We have a cluster with education, with Open University, Applied Sciences University, and some other schools mainly. We have a cluster around the central station in Heerlen, with a big new development of 50,000 square meter containing hotel and a big supermarket. We have a social housing cluster containing about 300 to 400 dwellings, and now we are developing an industry cluster in the northwest part of Heerlen, and this is the one where also our project is going. Well, what we try to do is we try to phase out fossils and replace them by green resources. And what we bring into the system is that we need more intelligence and that we need time control on energy flows. So that is 2 strategies that we try to apply. And then I will show you to what kind of concept this has led. If we look at the city and we look at renewable sources, we know that we have a solar irradiation of about 1,000 kilowatt hours per square meter. And if we bring the demand back, the heating demand to square meters in the city, then we know that we have about 20 kilowatt hours demand. So if we can make an efficiency of 2% on this solar irradiation, then will be enough to cover all the heating demand. In general, if we look at cities and strategies, we see this kind of graphs. They say we have actual energy demand. So if we bring back this demand by energy saving, and then we can address different segments like offices and dwellings and industry and agriculture. And on the other side, we raise the amount of green generation like solar, wind, and geothermal and biomass. And somewhere we will find a crossing point which should make this entire city or district energy neutral. Well, there is a big problem in this graph, and in fact, it's 3 problems. If we look at them, first, if the generation of energy is not in the same time and moment than the demand, then we have a problem in time. Also, we have a problem geographical, because if we have the supply at another geographical location than the demand, then we have to transport this energy. And the third one is we have to bring it to the right temperature. If we don't fulfill these 3 boundary conditions, then we never will reach this energy neutral point, which is, in fact, it's not my graph. It's coming from our ambition document, but I see this more often generic, that people think this way. They think if you just bring down energy and raise supply, then we will be energy neutral. Well, then looking at our grid in what we built it in the city of Heerlen, if we look at grids anyway, you can go from centralized grids to distributed grids or decentralized grids in between. What we are building, in fact, is a distributed grid, a cloud of connections which are mutual connected, just like we have seen in IT sector, where we started with the big server and went to a cloud of small acting computers and building some power together by all their combined individual power. Some remarks about these pictures. We have a hot pipe going in the city at 25 to 28 degrees. We have a cold pipe which is running at 16 to 18 degrees. So that are really moderate temperatures in regard to district heating and cooling. We do not have any fossils or gas in it. The only energy we use is electricity, so it's an all-electric system. We have the big mine water storage for seasonal heat. We build in storages district level for days and weeks exchange, and then we have the decentral building plants, which are always located in the building and only get active when those building has an energy demand. Those stations always work bi-directional, so if we give them heating, we get back cooling, and if we give them cooling, we get heating back. It's available to bring in surplus energy, and due to the low temperatures, any energy which is above 28 degrees, but even if it's below, because we use the backside of the heat pumps in the energy plant to bring it up, then we can bring this energy into the system and use it at some other place. Another thing is that the heat pumps that we have running, I'm sorry, I try to point, but I lose my pointer. There it is. Those heat pumps that we are running, feeded by water from 25 to 28 degrees, have a very high performance. They have COPs of 5, 6, or 7, and as I said, we also, if we give heat, we produce cold at the backside and bring it in the cold circuit. So if your neighbor has a cold demand, then even the backside of the heat pump is raising the COP of this energy flow. This is an artist's impression of our system, this backbone, and you can see this building. If this building needs cooling, then a pump will start and it will distract cooling from the grid. Then it will return heat. If there is another building in the cluster which needs heat, then their pump will start also, and they will distract heat and return cold. Then nothing will happen in this. I really have a problem with my point. Nothing will happen in the cluster basement to the backbone. It just will balance itself in this district cluster. If not balanced, then we get to the cluster basement and we exchange energy with the backbone, which also can exchange energy with other clusters. If one cluster has a heat surplus and another one a cooling surplus, then we can exchange that on the backbone. If there is an overall heat or cooling demand, then we go back to the mine water resources and we take heat or cold from the mines. This is a picture which is more or less showing the idea of what we do. In fact, we have 3 aggregation levels. So we have the city level where we have a source which might be somewhere between -10 and plus 25 degrees in our case. And we have a buffer connected to this level to equalize in time the energy demands and energy deliveries. We can do this on mine water, then we are really high temperature already, but we also can do this on an aquifer, and then we might take this energy from 10 degrees Celsius. There is a heat pump going from this level of heat to an area of temperature which is outside temperature dependent. So we bring it up from maybe 25 degrees to 45 degrees, which is done within the district or within the complex of buildings. This is a feature here where we do not yet have a storage, but we are working quite hard on that. That would be the large thermal storage, like Daniel told us about, and which would keep energy in the district, cooling and heating, and could be fed by industry surplus, by solar, thermal energy, or conversion energy, all kinds of incoming flows from this district. From this level of probably 45 degrees in the building itself, and that's mostly like a dwelling, we have a very small booster heat pump. It's about 500 watt electrical, which will raise the amount of water in temperature which we need for domestic hot water. And also in those dwellings we have the small buffer vessel of 150 to 200 liters, which might also be fed by solar energy. If the district buffer can deliver really high temperatures also, then we could make a shortcut and go directly from this district buffer on a 4-pipe system to the dwellings and bring the domestic hot water without needing the booster heat pump. The general idea of what we do, if we look at the total actual energy demand of a building, then first step still will be to save energy. So do some insulation measures and reduce the ventilation energy of this building. Then we have an amount of maybe 60 or 70%, which is needed to be supplied to the building. But we also bring in the cooling because we have to buy a directional system, and we think that buildings need a lot of cooling in future. And we add up low temperature waste heat. So by keeping the return flow from the cooling and the waste heat, we can reduce the energy amount back to about 35%. In fact, we say, let's say it's 50%. So we have a 50% energy reduction for buildings in city just by building this kind of district heating and cooling grids. And then we have the very strong heat pump operating at the CFP of 5, which will bring approximately for one dwelling in the Netherlands, that will be 20,000 kilowatt hours. We'll bring it back to 2,000 kilowatt hours electrical supply. And if we look at the demand of 2,000 kilowatt hours, then we see some light in the tunnel and say, okay, that we can solve this kind of amounts of energy just by solar panels on the roofs, PV panels, and we can find the solutions for that in an urban area.
Herman, a short organizational interruption from my side. So you're entering the last 5 minutes, just for you.
Okay.
Thank you.
Thank you. In fact, what we are doing by looking at this dwellings is that we look at the best renting, highest efficient investments on the building level, but combine those with the highest efficient measures on district level. So if we have 2 buildings close together, one heating and one cooling, like a supermarket and dwellings, and we can serve 200 dwellings by one supermarket, then there will be a very profitable investment in the district heating system to connect those 2 consumers. This is our business case. In the past, we had the district heating, and we spent a lot of money on buying fossil energy by investing in sustainable infrastructure. If we go to the right, we see that we only need little money for buying electricity, and we have about 19 euros per gigajoule, which becomes available as an investment space. If we look this at the national level for the Netherlands, where we have 300 petajoules in dwellings, then that will be an investment space of 6 billion euros per year, and if we count on 30 years, it could be 100 billions, which gives us an investment space of more or less 15,000 euros per dwelling, and there was also some extra space from avoided costs. Well, that's more or less the business case. We try to connect the dwellings between 15 and 20,000 euros per dwelling in parts of Limburg region. We have this ambition. The region has 250,000 inhabitants with 8 municipalities. They want to be carbon neutral in 2040. And if we look at the energy balance, then we see that we use 30 petajoules, which is about 550 million euros per year. And 89% of this energy money is going out of the region because we do not have fossil resources in our region itself. Then I have some pictures what we are doing in upscaling. This is existing connections that we have in the cluster A, this educational cluster, and we are now planning new connections in the next years to bring in this cluster and adding up all those connections to more or less 10,000 dwellings within the next 5 years. In fact, this is not just wet dreams, as we would say, but this is these are concrete projects where we are discussing a connection with those building owners. Then we have the same for the cluster B, which is the station area, and we see for the cluster C around social housing that we plan new connections also there for the next years. This is the industrial cluster, and now we are building this cluster basement, and we are extending the grid with the funding of Interreg Northwest Europe. And in fact, from the LIFE project, together with Euroc, we are connecting one of those industries to this backbone and looking at the skid and the energy plant, the substation, what would be best fit for this situation. We are also looking at the city of Brunsum, which is close to Heerlen, and where we do not have a mine reservoir. We just got funding from the Dutch national government of 4 million euros to take 2 districts of the city from the gas grid, and now we are planning projects around an aquifer and around large-scale atomic storage in the city of Brunsum to start from January next year. And another picture for the city of Kerkrade, which is at the other side of Heerlen. Then I have some final sheets showing you how this looked like if you come and visit Heerlen. This is a basement, a prefab basement, which we use for the wells. And then we have those standard skids inside them. The advantage of this way of working is that we can work very quickly in the city. Within 2 days we have this basement installed, and we will not disturb environment, and people will not ask us difficult questions about what we are doing. And also for the planning, it's very good to have this kind of prefab work that, you know, at this point everybody has to be finished with their own part so that we can bring it all together at one point in the timeline. Well, this is a cluster basement, more or less the same as the well basements. At the right, you see our mayor, who is come and visit us and is coming out of this basement, and you can see that he is really happy that we do these kind of things. Then we have the idea about connecting a district of dwellings, more or less 150 to 200 dwellings, by a specific sector basement with the skid also in it. We are working on concepts for high-rise buildings where we bring some column before the building, and where we bring in those installations which we need for individual dwellings. This is an idea how this could look like. In fact, in January we are making our first pilot dwelling to show this solution.
So Herman, here is again Marco. Sorry, I invite you to go to the conclusions if you can. So that
I'm just 5 more sheets, Marco. I'm nearly finished.
Okay, thank you.
The vessels that we will bring, that we already brought and bring in the buildings itself, some pipe work in cluster D, ongoing work. The skid which is built for cluster D basement, cluster basement. More pipe work. And connections between those pipes. And that's the end of my story. Thank you very much.
Thank you, Herman. So I take the occasion while we can introduce Christina Lignerud for the next presentation. I take the occasion to tell you that if you have questions even after the webinar, you can just write us by email, and we will be glad to answer. So again, a warm thank you to Christina, again outside from the FLEXYNETS project, to be available for this webinar. So I give you the word, Christina, and I know you will focus more on business models. Thank you.
Thank you. I'm just going to make sure that my screen is showing correctly. Okay, so thank you for giving me the opportunity to be part of this webinar. I'm here to talk about the ReUseHeat project and the first results that we have, and also give you some inputs about the project. So first you will get some information about the project, and then we have a deliverable that was delivered in November, where we have tried to identify the urban waste heat source potential. And by urban waste heat source, we have looked at 4 things. That is heat from sewage water, heat from a computer center in the cooling process there, heat from metro systems, and heat from a cooling process in a service sector building in a hospital. We have also got a number of stakeholders that we have conducted interviews with in 9 different countries, and we have first results from this. It's a deliverable for next year, but I will share our first indications. And we also have a deliverable for next year on business models, but also there we can share some thoughts with you. So as you know, there is a big energy use for heating and cooling in the EU, and there is an ambition to decarbonize Europe, and this is also where ReUseHeat comes into the picture, and it's in line with the strategy on heating and cooling at the EU level. And what you often do is to make some kind of building renovation, increase the renewables, and involve the users. So our scope is on the waste energy segment, and then we have looked at the urban waste heat sources, and we include them into existing district heating networks. And we basically do 4 things. We have 4 demo sites. We look at the business models and contracts, and we monitor and evaluate the outcomes. Let's see. So my screen is not shifting now. Why is it not shifting? Okay.
Yeah.
Here. So our objective is to demonstrate first of their kind advanced modular and replicable systems, enabling the recovery and reuse of urban excess heat. And here you have a picture from our proposal with our vision of the future smart city that actually uses a lot of heat to heat itself from these sources that I mentioned. And again, technologies, business models, and contracts. We also try to evaluate the investment risk, and we look at the bankability of this kind of investment. And we will have, as our main deliverable in the project, a handbook showing how to invest in low temperature district heating schemes. And just a short note on the 4 demo sites. In Germany, in Brunswick, we have a computer center, and we take the heat from the data center, and we will heat around 400 newly built passive houses or low energy houses. And this solution has a link to the existing district heating network for safety reasons. In case the heat delivery from the data center is not sufficient, then we can have a backup from the existing network. Then we have another demo site in the city of Nice in France, where we have the connection also to a new low temperature district heating network. Here we are trying to work with the customer side, and we are sensibilizing the end consumer with a large display showing how much energy is coming in real time from the sewage water. And this one will then be mounted in the entryway of one of the buildings. Then we have the hospital. Here we have seen a large potential because this kind of heating and cooling exchange is usual in the service sector buildings. Here we have then the largest hospital in Madrid, and they have a need for cooling all year. And we take heat from this cooling process and use back for the heating purposes of the hospital. And then our last demo site is to recover heat from the tunnels and platforms in the metro system. We have heat coming from people moving around, from ventilation, and from the braking and starting of trains. And here we will recover the heat from the platform. Yeah, so that was basically very short, the main contents of the project. And we have made one deliverable already on the potential of waste heat sources in Europe for the EU 28. So we have looked at the wastewater treatment plants, the metro stations, data centers, and service sector buildings. And we have looked at available excess heat and accessible excess heat and made a distinction. In many potential studies, this has not been done before, but we try to make a distinction of the heat available at the heat pump evaporator and heat accessible at the heat pump condensator. And the results that we find is that there is a lot of energy out there. So in petajoule per year, we have about 9.6 for the data centers, 3.9 for metro stations, 12.9 for wastewater plants, and 25.7 for the service sector buildings. And then we have also added available excess heat from hot temperature heat sources, which is then 17.8. So we have a very large total for Europe, and we see also that the metro stations is the one with the lowest potential, whereas the service sector and wastewater plants seem to have the highest potentials. Then if we move to our stakeholder interviews, we have made interviews with 5 groups, and we identified that 5 stakeholder groups were very relevant to this kind of investment. So we have talked to district heating operators, policymakers, investors, end consumers, and heat owners. And we find that technology is really not a problem. It's not a technical barrier that we see. The only technical problem that has occurred in the discussions is that it's sometimes difficult to find the right heat pump, but it can usually be managed. What is a larger barrier or problem is that the maturity of urban waste heat recovery solutions is low, so we need demonstrators. both amongst customers, they don't really know, the end consumer doesn't really know that they can obtain this kind of heat. And then also in terms of regulation, urban waste heat sources are not seen anywhere and there are no incentives for them. So the maturity is low and that's a problem. When we talk to the stakeholders about replicability, they all say that it seems to be a high replicability potential because every city has this kind of heat sources. Then the legal framework is not in place for this kind of waste heat recovery, which is then a barrier. There is nowhere any stipulation on how to treat this kind of waste heat, for example, compared to conventional waste heat. This is particularly a problem in countries like Denmark, where there is a taxation on waste heat already, and then not having this differentiation makes the business even more difficult. In regards to the permitting procedure, there is no standard procedure for this kind of heat source, which is a barrier. As I mentioned, we have made an analysis of many countries, and we have seen that, for example, in Romania, there is no permitting for this kind of waste heat, which means that you would have to apply for permits similar to the ones of producing and selling electricity, which is a very advanced procedure of getting. So that would be a major barrier because the permitting procedure is then not very up to date. Then we addressed the question of existing district heating networks, if they allow these kind of low temperature urban heat sources. And that's then a large challenge for the district heating companies. It depends on the site, what temperature is okay, but usually you can solve it with a heat pump, but it's still an issue. And then we found that there is no incentive to this kind of investment from the policymakers. There is a lot of incentives on renewable energy sources, but no incentives for urban waste heat recovery. So that is also not very beneficial. Then we came to the Legionella legislation, which is really not an issue because you don't use these heat sources for the end consumer. You include them into the district heating network in our demo sites. And then there were other questions about the low awareness, no standardized contracts or business models, and the fact that you need to give your district heating business an update if you want to engage in this kind of activity. If you shift from large-scale production and distribution towards a multiple of small heat sources that are lower in temperature, you need to shift your business model and business logic. And the maturity for this is very low amongst district heating companies. And then if we go also to some thoughts on the business models, here we are really working right now on identifying what contracts would be suitable according to theory, and then we try to apply it to our 4 demo sites. And for contracts, we see that the length of the contract is very important for this to work. It has to be at least 10 to 15 years, because otherwise there is too much uncertainty about the heat delivery. And this is similar to conventional industrial waste heat recovery, but it seems to be more important with these urban waste heat sources. Another component is the renegotiation clause. It appears to be very important to be able to update in real time what the waste heat recovery looks like. So a renegotiation clause is important to account for changes. And then a major obstacle for this kind of investment is that it's unclear of who should own what. And that's the same as we have for conventional industrial waste heat recovery. But here it's a question of who should own the heat pump, and how far should the responsibility go of the district heating company. In terms of business models, we see that this kind of demonstrations are made because there is a value of green. However, nobody is really willing to pay for this green value in the end consumer position. So that's a big question then. How do we get the value of the green dimension? This kind of urban waste heat recovery makes it possible for the district heating company to come closer to the customer. The customer might even become a prosumer. We talked about that earlier today, who also sells heat into the system. In our demo sites, we discovered that they were really focusing so much on technology that all these things in the business side of coming closer to the customer and the value of green, they didn't think of this. It was a secondary problem to them. And then we talked about the heat pump a lot. The inclusion of the heat pump, does it really alter the business that is at place? And the dependency to electricity is increased. How does that impact the business model? We don't have any final conclusions yet, but we have raised these questions. And a first conclusion is that the urban waste heat recovery, it's like the next generation of heat recovery. It necessitates a more precise business with digital control systems, allowing for peak shaving, using houses as storage and things like this. And this puts then a larger pressure on the existing district heating business to develop. And what we see in our demo sites is that this is not really done. So what is done is a test of technology. Yes, and this was my presentation. Maybe a little bit short, but more room for questions.
Yeah, thank you. Thank you very much, Christina. Indeed, it was nice to, let's say, recover a bit from our delay. I've seen a question for Herman, but maybe we can answer this at the end of the webinar. So for the moment, I would go on and give the work to Dirk Pietruszka from Enisys for the last presentation about FLEXYNETS, namely the part on control. So thank you, Christina, and welcome to Dirk.
Hello, everybody. I try to start my presentation.
Sorry, are you already a presenter, Dirk, or not yet?
Yes. Yes, I am.
Okay.
Okay. Can you see now my presentation?
Yes. Yes.
So, hello again, everybody. So now we come back to the FLEXYNETS project. It was very interesting projects which are really running and which are analyzing it more on a structural basis. And so I come back to one important issue, which is about control. How can such systems be controlled in the future? That was one of the main topics also within the FLEXYNETS project. I don't know. Okay, now it's moving, I guess. Okay, so what we are facing in the thermal grids is something which has been also faced within the electricity network. So we came from a centralized energy production supplying heat to distributed buildings with one central energy system, and now this moves towards a system which is more distributed. So we have some central systems, but we have also distributed systems which also take heat, but also bring in heat to such a network. And this also changes the control, of course, of these systems, because the classical control systems won't work anymore. So and therefore we need to see how we can operate the systems as efficient as possible. So as you can see here, we have distributed consumers, but also prosumers, which are taking heat, but also bringing in heat. We have heat pumps, which take out heat. We have chillers, maybe, which bring in heat and take out and produce cooling energy. And this makes it quite complex because within the network we don't have constant pressure levels, for example. So, and also the question is how we can organize all the sources to keep a certain network temperature. But the system becomes even more complex if you see that there are also interactions to the electrical network. So we have, of course, GHP units centralized, but also decentralized. We have chillers and we have heat pumps who are consuming electricity. And we have also the gas network. So if you look at GHP units, they also consume gas. So there are interactions on different levels which need to be organized. And the question which we addressed within the FLEXYNETS project was, how can we manage such a complex system? What you can see here is the structure which we have developed and set up also in our control system. So classically, you have a high-level control for the centralized system and for the pump control of the thermal network, and you have also, in some cases, some control on the distributed systems. But now, if you have also distributed energy producers and consumers, we need to have something more intelligent. Therefore, we introduced a new level, a management level, a strategic control level, as we named it. So in this level, we have some data management, of course, but also optimization tools and simulation tools which are forecasting the demand within the system, but also the production of energy within the system from PV or from solar thermal systems and so on. And for this, we also need, of course, weather forecast data. We need to know what is the actual situation in the network, and we need in future also to know what are the electricity prices in the next few hours, if we have flexible tariffs, which will come in the future. The same is true for gas networks. So there are a lot of dependencies in such a system which need to be organized. And the way it is organized is we need to have forecasts for loads, but also forecasts for the production. And we know that we have some flexibility in such a system. Main flexibility comes from storages, could be electrical storages. But in thermal networks, the main interesting part is the thermal storages. So this can be technical storages in the different buildings, but could also be the buildings themselves. So if we change the room temperature by 0.5 degrees, we have already a quite huge storage potential, which could be used. And this flexibility can be used to adapt the operation, for example, of heat pumps, of chillers, and to change it to times where we have, for example, a lot of PV electricity available or cheap electricity prices in the electricity grids. And this flexibility can also be used to stabilize the electricity network. So if there are peak hours where a lot of electricity is consumed and we have not enough sources, then we could reduce our energy consumption. And on the other hand, if there's a lot of electricity in the network due to high production by wind energy, for example, then we could operate the systems during such times. So the flexibility comes mainly from the storages which are available in such a system, and how to activate them really needs some forecast of loads and also of energy production, energy prices, and then we can develop within an optimization loop some operational schedules for all the different suppliers, consumers, prosumers within our networks to keep it at a certain network temperature, but also with the goal to operate it at the highest possible efficiency. So how we made this in practice is that we developed a kind of a optimization level which has been integrated. This can be a server which is on-site, could be also a cloud solution where we have all these optimization tools running, and this communicates with a high-level control of the thermal network, which also controls as contact to the substation controllers, and can then pass through these optimized operation schedules, and the systems try then to operate their subsystems according to the optimized schedules as long as possible. Of course, there are also some limitations because we have some accuracy problems anytime. So because a prediction is just a prediction, and it can vary from the real situation. So therefore, there are also some safety modes to keep the systems in a certain range to ensure that the people have enough heat at any time or enough electricity. So, but as long as possible, these controllers try then to follow these optimized schedules. They are updated every hour, these schedules, by the actual situation measured from the substations. But as you can see, this becomes a quite complex problem, also a complex problem to optimize. And how this is done is a very simple scheme here. So we have the optimized, we have some simulation tools predicting demands, forecasting energy production, and we have some optimization tools to arrange the demand, considering the storage capacities according to the energy production and also to electricity prices, and then to find an optimum, could be financial optimum, economic optimum, or also environmental optimum, the lowest CO2 emissions. And this results into an operational schedule, which is then passed through the control. This tries to operate the systems accordingly, and then, of course, there's some feedback to the optimization from the real systems, and the systems operated again and again to ensure that we are really operating the real system and not going far away from the real situation. This is more a technical scheme, how this can be implemented. So this forecast, this is all these simulation tools. Then we have here the current state, which comes from this operation system. They send signals as a current state. And then we have this planning. This is the optimization within the system, which really develops these operational schedules. They are passed to the real-time control. This tries to follow the schedules and controls the system below accordingly. So, and of course, there are some feedbacks, and we have also some safety modes to really ensure that the systems are operated in a good way, and also to satisfy the people living in the buildings in each situation. So if this is not the case, then they leave the schedules and operate systems independently. So, but of course, you see that this is a quite complex task. So we did a lot of work on this simulation task. We worked with dynamic simulation models, so real physical models, but found out that these models have a quite long simulation time, because you need to do a lot of optimization loops. Then you can imagine that the simulation time will expand to a number. If your system becomes bigger and bigger, this can be a problem. Therefore, we start also to look at some other systems, some neural networks, which we can train with maybe simulation tools, but then they are operating much faster in the optimization phase. We didn't develop it to the final end, so we did some tests on some systems, but there's still some, I would say, further development needed to really bring this in practice. So this is a really high complex task to have accurate enough predictions of loads, and also to organize these optimization loops for larger systems correctly. Therefore, we have also an additional project, the Life for Heat Recovery project.
Dirk, unfortunately, okay.
Yeah, someone muted the microphone, I don't know why.
Yeah, your audio was not well for a second, but now you're back.
Okay, so I don't know, the system's muted my microphone, I don't know why.
Okay, sorry.
Okay, so, and but what we did also in the project with or URAG, together with URAG, there have been done some also simulation work to see how we can use, for example, heat pumps as a flexibility tool to make some load shifting from peak hours to hours with low peaks, and to see how we can optimize the overall cost, of course, but also to avoid peak loads within the electricity network. And there have been done several examples where we did some calculations on this. And what we found out that we really increase a bit, of course, the electricity consumption by only 2% in this case, because we have higher temperatures, for example, in the storages. But we significantly can reduce peak loads within the district heating network by 20%. And but in the overall, the reduction of costs was quite low in this case. But it always depends on which are the assumptions you need or you consider in these simulations. But it shows that the cost saving is maybe not something which is reached easily, because we have, on the other hand, if you increase temperatures, then you decrease efficiency in your system and have higher electricity demands and also higher losses. So that this compensates somehow, and sometimes also the cost savings. But what is also quite interesting is if we have PV systems installed in the system, then we can shift the heat pump operation into time. So we have high PV production, and then use this on-site generated electricity, which is quite cheap. And then we can also get quite good economic values. Yeah, but these are just some examples showing how this could operate. Well, so how does it look like in the real implementation? So this is one of our controllers, the substation controller, which controls a heat pump, some storage, the heating circuit in the building, and the hot water production. So as I said, we can use this thermal storage as flexibility, but also if we increase the room temperatures, we can also use even more storage capacity in the buildings. And what we get from the optimization system, we get these operational schedules which are optimized for the whole system, and then our controllers try to follow this control of the heat pumps to avoid peak loads, and also to shift to hours where electricity prices are cheap, and we use the thermal storages to manage it. And but what we implemented in our system was to really be able to operate according to schedules, also to set up this optimization server and cloud-based tool where these optimized schedules can be prepared and analyzed and then sent to these controllers. But all this process, of course, we need to be.
Dirk, here is Marco, and from you are entering the last 5 minutes.
Okay. So main results for the control. So the control of the co-district heating network and the interaction with electricity and gas networks is highly complex, as I've shown. Thermal storages offer flexibility, which is interesting, which can be used to operate the systems more efficiently. Simulation-based predictive control and optimization tools can help to significantly increase the overall performance of such systems. And the question is always which is the optimum we want to reach. Is this an ecological optimum or a financial optimum? It's not in all cases the same. So sometimes ecological optimum is not equal to the environmental optimum. So that needs to be selected what we want. We can use the system for peak load shaping, of course, and increase PV own consumption in such districts quite significantly. I have one short example which I would briefly show. So this is a co-district heating network, quite small size, with 25 single-family houses connected with a geothermal source. It's a collector on the agricultural field in 2-meter depth, and this provides low temperature heat to this district heating network. we have constructed the field a bit small due to some problems with the owners of the land. But we have also some waste heat sources which could be used, which are not integrated yet, but could be used. It's some waste heat from a supermarket, which can be easily integrated into this system. And we have also some waste heat from a wastewater channel, which we want to integrate into this network. This is part of the Life for Heat Recovery project to do this. And so it's a quite interesting system. It started its operation in 2012. Now we have some years of experiences. Of course, not all buildings were there, but now it's nearly fully constructed, as you can see in the next picture. This shows how this geothermal collector is integrated. So it's just a special tool which plugs in the tubes in the 2 meter depths into the ground, and then you activate the ground, and you have some collectors at the beginning and at the end of the field, which are then connected to the cold district heating network. Quite interesting system. As the time is running fast, I go a bit faster. So these are some pictures of this district which has been built and which is supplied by this cold district heating network. Here a scheme. Of course, we have heat pumps in all the buildings. We have PV system on the roofs, and we have also batteries in some of the buildings. And here you see some operational measurements of the supply temperature, which comes from the cold district heating network. As you can see, it's not constant because we are using the ground in 2 meter depth, and it depends on the seasonal conditions, which temperature you can extract from the ground. So it varies between roughly 15 and 1 degree supply temperature, which can be provided. And of course, it depends on the outside temperature, how deep this goes. What you can see here is the average COP of these systems. So you can see it varies between 4 and 5. So we have in all these buildings, we have different heat pumps, different hydraulic concepts, which makes it quite interesting, but also quite complex to monitor it and to analyze it. Here we have also some very low COPs, but there we found out that the heating meters were not operating correctly. So they are also in this region of 4 to 5. So it's quite good performance which can be reached. We also faced some problems, of course, but this was a quite interesting problem which we were faced with. So we have this cold district heating network. You see this is the supply line from the cold district heating network. This is a return from the heat pumps to the network. And what you can see here is some icing on the supply line, and this was a bit confusing because normally this shouldn't be iced, but this should be iced. So it was in the early stage of the operation, therefore there was no isolation and we could see it. And then we thought, okay, maybe the heat pump is connected wrongly to the network. So they exchanged supply and return, but this has been checked by a mechanical person that everything was correctly connected. But then the service engineer came from the heat pump provider, and they recognized that they just put the wrong description on the heat pumps in the production. So they named supply with return and return supply, and therefore it was really wrongly connected, but not. It was due to a wrong description. But what happens is the interesting thing. So as this was at the very end of the network, there was a kind of a circulation between 2 heat pumps at the end of the network, and we had nearly no geothermal source available providing heat, only this short network part, and this resulted in the situation that the temperature dropped quite significantly and quite fast to -9 degrees, and then we stopped the operation of the system. So this shows that also some problems can happen, and in these systems, although there was a very good maintenance and everything done. Shit happens also in these systems, but this was quite interesting and can be, of course, avoided in the future. So what we found there was really promising results. So we have quite high COPs of the heat pumps. We have a quite good performance of this ground collector. We are still optimizing these heat pumps. What we found with these different heat pumps are that they show very different control behavior. Some switching on and off permanently, some operating more constant. And this also leads to a difference in the COP and the performance of the systems. So in future, we will look more closer to this system by we started our intensive monitoring phase in autumn 2018, so we get some more information also from this system. And why I presented it here, we use it also in FLEXYNETS as one of the early adopters to show how the system is operating. So that's everything from my side, and thank you very much for your attention.
Thank you, Dirk, for your presentation. So we are now at the end of the webinar. In the meanwhile, we got a question, so a specific question for mean water. It's about the primary energy factor of the network, if it was calculated, and if so, if you can provide an estimate. In the meanwhile, so please, Herman, if you want to switch on your microphone and start the answer, if you can. In the meanwhile, I will show some slides for conclusion, just to yeah, make some short summary about what we presented today.
Yes, thank you, Marco. Well, it's a very good question, because we have quite some problems to calculate and estimate the performance of our system. If we go to these three different areas which I mentioned in one of my pictures, then you could, if you look at the district level with the mine water reservoir, then we get some COP around 20. If you look at the heat pumps which are at the district level, they might run at approximately 6 or 7, and we have the booster heat pump, which is doing more or less 3.5 on their COP. But if you add them up together, you might get quite a very good performance on primary energy. The most difficult point is that every change in the system, as we have this cloud system with dependent on behavior and performance of all end users, that every change in the system will bring some change in our performance. At least what we see, if we have over the year heat demand, which is normally the case in the Netherlands, then we should add some real large resources to get heat from this. Could be from the mines, but even better from deep geothermal. Of course, the waste, the heat. Also, what Christina is pointing at, those sources like jewelry and maybe subways and this kind. If we can collect all this kind of flows, then we will have more than we need for all the buildings, and then you could end up with quite a very good performance. Now, for Dutch regulations, we calculate on EOR of 2 on primary energy. So if we take all the electricity from the power grid, which has an efficiency of 40%, then still we can get an overall performance of 2. So every kilowatt hour will bring us 2 kilowatt hours of usable heat.
Thank you, Herman, for the kind explanation. So a very efficient system, I would say. So it's now time to close. So we'll just take a couple of minutes. So we'll be very fast. So I'd like to leave you with some message about the FLEXYNETS project and about all these, let's say, low temperature networks with decentralized heat pumps. Just as a very short summary, some crucial enabling factors from our point of view. So the first one is the large availability of cheap, low temperature heat. Because, of course, in the case of availability of high temperature heat, it's questionable the use of heat pumps. This is the case, of course, for example, for mean water, but in all the promising scenarios we analyzed, we always assumed a large availability of low temperature heat. It can be waste heat, it can be geothermal, but this is the main crucial points. Of course, also cooling needs are very helpful for these networks, and on the other hand, these networks are helpful for cooling needs. This is something which is expected to become more and more important in the future. It's already quite important for Southern Europe climates, so this is another key aspect. And the final point, which is worth pointing out, is the availability of affordable electricity prices. You see in this plot some prices for some European countries: Denmark, Spain, Italy, and Germany. These are industrial electricity prices without taxes, and this also makes a lot of difference. What's interesting to see is that there is almost a factor of 2 between the lowest and highest values. So, of course, since electricity consumptions are one major item of cost within this system based on heat pumps, this is an important issue, and not all the countries, let's say, are equally favorable from this point of view. Daniel showed some cost splits. It emerged that some items are very big, like, for example, the cost for heat pumps themselves. There is, of course, some room for improvement here. We think that the economy of scale or the presence of some small backup could be very beneficial from this point of view. Also concerning the extra electricity costs, some countermeasures could be to have business models with give rise to industrial electricity prices, which are lower than residential electricity prices. So this would imply that substations, even residential substations, are owned by the network manager, which is the case in some of the networks met in our surveys. The fact that low temperature waste heat is available and cheap is, of course, crucial. And the last economic comment I would like to do is about seasonal storage. That can be very beneficial from the energy balance point of view. As Daniel pointed out, the low temperature difference between supply and return in FLEXYNETS make the storage density less smaller, sorry, if used at these temperatures. So in this case, maybe higher temperatures or different solutions could be used. From this point of view, of course, some geothermal systems like the mine water one or even boreholes, which provide simultaneously a source and a storage option, might be even more convenient. Of course, apart from economic estimates, the entire point here is about environmental convenience of this solution. And again, from this point of view, the presence of large amounts of waste heat are crucial. So here I showed a few estimates for individual solutions, standard district heating solutions. The blue bar corresponds to some individual cooling, and some FLEXYNETS solutions with different percentages of waste heat. And of course, here the potential to bring down the primary energy factor is very big. So in the end, I think the one thing I want to point out here is the importance of recycling energy rather than producing additional energy for new application. This, of course, relies a lot on waste heat. Several sources were identified. Our opinion and expectation is that it's difficult to find a single source, a single low temperature source which can satisfy the needs of a large network, but typically several of these sources are available in a lot of urban contexts. So combining multiple sources can satisfy big loads, and it's something which has to be taken into account with all the consequences on the control side. And concerning the industrial field, let's say the integration of low temperature heat seems also beneficial in terms of the interaction with companies. They seem less suspicious when they are asked to be integrated at the level of cooling towers, for example, rather than at the level of flue gases, which are closer to processes and so on. The price of waste heat in some cases can be even zero if the companies providing that have some cooling benefit or even understand the positive image deriving from helping to achieve a more sustainable society. What is still missing is some standardized technical solutions to have like plug-and-play solutions to our companies and really be able to have quick installations of these waste heat recovery systems without affecting their production or being very fast during their, let's say, holiday periods. And the same thing on the business side, because having trusted business models with clear contracts, as mentioned by Christina, also in terms of duration and so on, is very important to set up this business. Besides FLEXYNETS, several other projects are dealing with these aspects. Christina and Herman provided some examples of that. Other projects are being followed by Enisis, Planenergy, by Euroc itself. So my final comment is just to stay tuned, look at the final updates on the FLEXYNETS website, where the final reports will be uploaded, and news concerning coming projects and so on will be regularly provided also in the next months. So again, a warm thanks from my side to all the speakers. I don't see other questions, but again, as said before, we are available by email in the case of some questions might arise even after the webinar. So that's all from my side. Thank you, guys.
Thank you. Bye-bye.
Thank you. Bye-bye, everybody.
Bye-bye.
Bye. Thank you again.
Last Christmas Day.